Membrane potential and answer the questions: what is a resting membrane potential? What creates it? What is used to calculate it? And what maintains it? Hello, everyone. My name is Dr. Morton, and I'm the noted anatomist. It would be difficult to exaggerate the significance of this transmembrane electrical potential difference we call a resting membrane potential. That we'll see it as this like negative 90 millivolts on the internal surface of our cell membrane. This electrical gradient exists in every single one of our 70 trillion cells. It influences the transport of every one of those cells, the driving force in the movement of sodium and therefore water, and it's essential in the signaling process. I just wanted to mention that at the beginning about how important this resting membrane potential is for every medical student to learn. Now, let's begin by answering the questions: what is a resting membrane potential? Well, it's the electrical potential difference across the cell membrane when the cell is in a non-excited state. So resting, the cell's at rest. Membrane, the differences in ion concentration across the membrane, inside relative to outside the cell. And the potential is caused by the separation of ions across the cell membrane, which creates the electrical potential energy measured by voltage. So resting membrane potential is also called RMP, or resting potential, or even resting VM. How is resting membrane potential measured? Well, we measure voltage at one point inside the cell relative to another outside the cell using a voltmeter, where we have a microelectrode and a reference electrode, where we measure the voltage using the microelectrode with respect to the reference electrode. So we take a look at this bathing solution. We measure the voltage at one point with respect to another. There's no potential difference or in between the two, so the voltmeter reads 0. Now, let's add a cell. And what will happen when we place the microelectrode inside the cell, with reference outside the cell with that reference electrode? So you ready? There's no potential difference, but watch. Now there is a difference in potential. No difference because they're both outside, but shing, as soon as you put it inside that microelectrode, it measures a difference. The inside of a cell is more negative than the outside, and it registers as more negative on a voltmeter. So that is our resting membrane potential. We also show this in a graph where you see it's measured in 0. It's not polarized. The microelectrode's outside in the bathing solution. Now watch, it is now polarized and then not polarized. And so the resting membrane potential measures at negative 80 millivolts on that graph. Now let's add the sodium channels like that, where there's a higher concentration of sodium outside, and these channels are going to open to allow that positive ions to go in to the inside of the cell. But remember, the inside of the cell is more negative, so it measures as negative 80 millivolts, and it shows as polarized on that graph. So what happens to the resting membrane potential when we open the sodium channels? It opens. It allows for this small amount of sodium to rush into the internal surface of the cell. So the inside of the cell membrane has received more positive ions, which then measures as positive 40 on the voltmeter, and it shows that we go from negative 80, and it depolarizes because it becomes less negative. But then we close those sodium channels, and the sodium-potassium pumps restore the concentration of sodium outside and potassium inside the cell, and so we repolarize. So we now have more positive ions outside relative to the inside, which shows negative 80 millivolts on the voltmeter, and we have repolarized this membrane. How do we get a resting membrane potential at cell membranes? Well, I'm going to do my best to attempt to show this using some schematics. Remember the salty banana, a lot of sodium outside compared to the large amount of potassium inside. Let's focus on potassium for a moment. Potassium wants to diffuse down its concentration gradient, but the cell membrane is not permeable to ions. Now, the resting membrane potential is established by ion concentration and, this is important, ion permeability across the membrane. So how can an ion permeate the cell membrane? We put a door there. We call these membrane transport proteins. This is a potassium leak channel. Now, the potassium ions can move in either direction through this leak channel, in or out, and that's based on concentration gradients or electrical gradients. Okay? So potassium moves from high to a low concentration. But remember that potassium ions are bonded with negatively charged anions. So when a potassium ion diffuses through down its concentration gradient through this potassium leak channel, the negatively charged anion is left behind because it cannot diffuse through this very specific potassium leak channel. And so we have a positive ion outside, negative ion inside. And what we see is as follows. We keep having these negatively charged anions left behind. So as positive ions move out via leak channels from high to a low concentration, the negative anions left behind make the intracellular membrane more negative. And remember that ions can move in either direction through the leak channel. So positively charged anions like potassium can actually leak back when there's a stronger negative charge. So as positively charged potassium ions diffuse out of the cell, positive charges accumulate on the outer surface while negative charges accumulate on the inner surface, those anions left behind. This difference in electric potential continues until the efflux of potassium has stopped or no net potassium ion movement occurs across the membrane. This is the potassium equilibrium potential. That was fun, wasn't it? Let's do it again. So what we see is that we have a high potassium concentration inside, which drives or wanting to drive potassium out of the cell. But then as you drive potassium out and you leave these negatively charged anions behind, there's an electrical gradient that wants to pull potassium back in. So what we have is an electrical or electrochemical gradient. The chemical forces and electrical forces are now in balance. By chemical, I mean concentration gradient. We call this the equilibrium potential or Nernst potential. The amount of potassium going out equals the amount of potassium going in. So the equilibrium potential is based on concentration gradient and the permeability of the ion at that membrane. Now, what electrical force is needed to prevent potassium from leaving the cell? Well, let's do a little experiment, a thought experiment. We have a cell with a high intracellular potassium. Lots, and each of them are bound to an anion, negatively charged anion. And there's no extracellular potassium. What would the electrical chemical gradient look like? Well, there's a really strong concentration gradient wanting to push potassium out of the cell, and there's zero electrical gradient because all the charges are paired. So we're at 0 millivolts for membrane potential. Now what happens when we introduce only potassium leak channels? So watch what happens. Potassium leaks out, leaving a negatively charged anion. We've gone to negative 20 millivolts. The concentration gradient has dropped a bit, and we're starting to get an electrical gradient. And we do it again and again. So we're seeing the concentration gradient is starting to diminish because we're putting more potassium outside, but our electrical gradient is growing. And so what we see then is we get to this point where the concentration gradient and the electrical gradient are in balance. The electrical and concentration gradient are in balance, and that happens at negative 88 millivolts. This is the equilibrium potential, or the Nernst potential. It takes negative 88 millivolts to prevent potassium from diffusing out of one of these cells. Now, when this occurs, we take the voltmeter and we stick it inside and look. It goes from 0 to negative 88 millivolts. That's how we can determine experimentally what that membrane potential is. How is that resting membrane potential calculated? Well, we do this through the Nernst equation. Helps us to determine what the resting membrane potential is. And this is showing the membrane potential in millivolts. And then that 60 is the ideal gas constant times temperature over Faraday's constant. From here on out, I'm just going to put 60. And it's the log of the concentration of the ions outside relative to the ion concentration inside. So let's try that with potassium, okay? So there's our membrane permeability. So 60 log of potassium outside, which is 5 millimolar, to inside 150 millimolar. So we do the math and we get negative 88 millivolts. Cool. What about like sodium chloride and calcium? Well, there's our potassium, negative 88 millivolts. So there's sodium. We take the outside and inside. So outside's 142, inside's 10. That gives us positive 69 millivolts. What about calcium? Well, we then do the math and you get positive 111 millivolts. And what about chloride? You do the math and you get positive 85 millivolts. Why is it positive? Because we have a negative charge on that chloride. All right, so let's put inside, and there's our different membrane potentials of potassium, sodium, calcium, and chloride. So to determine the resting membrane potential, do we just add these numbers up and see what the total is? But because we need two things to determine resting membrane potential: concentration gradient and permeability. So the concentration gradient, we have a lot of potassium inside, so it has to drive to the outside, and sodium, calcium on the outside, and it wants to go inside. But there's also permeability. And so the ions moving across the membrane, 90% of all the ions moving across the membrane at rest is potassium. Whereas only 1% sodium, 1% calcium, and 8% is chloride. And so we take 90% of negative 88, that gives us negative 79 millivolts, and 1% of 69 is 6.9, and of 111 is 1.11, and 8% of 85 is negative 0.68. We now add those up because it's the concentration gradient and the permeability, and that gives us a resting membrane potential of negative 84 millivolts. You're like, but wait, that's not exactly what we talked about before. Hold that thought. Because now, how do we maintain this resting membrane potential? Well, it's through the contribution of the sodium-potassium pump. So we have a lot of potassium inside relative to outside, a lot of sodium outside relative to inside, and we add this sodium-potassium pump, which is primary active transport because it uses ATP. It'll take 3 sodium ions from inside the cell. ATP will make a conformational change and pump these 3 sodium out against its gradient, taking 2 potassium and pumping them into the cell against its gradient. And so there are more positive ions, 3 sodium, pumped out than in, which is only 2 positive. So it makes the cell exterior a little more positive and the cell interior a little more negative, because for every 3 positive out, there's 2 positive in. So this resting membrane potential negative 84 is really negative 90. Now so when you're adding or removing ion channels changes the cell's resting membrane potential depending on the type of cell you have in the body. So a cardiac muscle cell is about negative 90 millivolts at rest, whereas a skeletal muscle cell is like negative 84 millivolts at rest, or a neuron's negative 60, or an adipocyte is negative 40 millivolts. So a resting membrane potential arises because of the concentration gradients for sodium and potassium across the membrane and the permeability of the membrane to these ions, with potassium being the most important to establish this resting membrane potential. And the gradients of sodium potassium are produced by the sodium potassium pump in all of our body cells. And this process develops and maintains the outwardly directed potassium gradient and the inwardly directed sodium gradient. And that, my friends, is resting membrane potential in a nutshell.